And we'll just wait a couple minutes for everyone to get here. But for those of you who are here while you're waiting, we'll be going over a lot of questions on the practice quiz one. So just be thinking about any questions you had on any of those problems. So we can go over some of those when we get ready to start here in about a minute. So there's still some people rolling in, but we'll go ahead and get started. So if you have any questions on any of the problems on practice quiz one, if you just want to go ahead and type in the chat what question number it is, then we'll kind of go over the problems that it seems like a majority of people had questions on. So if you just want to go ahead and type the number of the question or the problem that you had, then we can kind of start to go over some of those. So Jordan, is today only going to be quiz? No, we do have one problem that I definitely want to get to. It's a proof by cases problem. And so that'll be kind of helpful for some of the later homeworks. So we'll definitely save time for that. But besides that, primarily to spend some time kind of going over some of these practice quiz questions, just to get ready for that quiz one on Tuesday. And then, so if anyone has any questions on any of the practice problems, you can go ahead and type in chat, and we can start to go over some of them. All right, so Andrew asked, what's a good way to see patterns for closed sequences? Yeah, so we can kind of go over some of that. One thing we could do is we could look at the practice quiz problem number 6. That is kind of along the same lines. And then just before we get started, so there's a question, can we expect quiz 1 to have the same length, same amount of questions as the practice quiz? And it should be about similar. It might be a little bit longer, might be a little bit shorter, but it'll be pretty similar to the structure of the practice quiz. Okay, so yeah, this was the hardest question for me. Yeah, so we can kind of go over this one. This is definitely a tricky question. So when we're looking at these sequences and trying to find, especially like for this one, where we're given nothing about the closed form, the recursive form, these can be a little bit tricky, but we kind of want to look for patterns in the sequences, and you just got kind of better at that with some practice. So what I like to do first is to kind of get a sense of how the sequence is growing or changing over time. So what we can kind of look at is we can look at the difference between each successive value. So between 1 and 5, we've got a difference of 4, a difference of 2, a difference of 10, of 14, and of 34. So we can kind of see that besides this kind of weird one at the start where we go down from 4 to 2 and then upwards, we kind of see each time we're kind of growing up quite a bit larger than previous times, especially the jump from 14 to 34. So this gives us a possible sense that this isn't just a simple addition or multiplication that's going on here, that this is some kind of exponential, just based on looking at, especially between 31 to 64, we have these really large increases. So that gives us a sense we're going to be looking at something of like an exponential form. And so some of the main exponentials that you should be familiar with and the patterns to be ready for the quiz are what 2 to the power would be. So for 2 to the x, we've got, for x is equal to 1, we've got 2, 4, 8, 16, 32, 64. For 3, we've got 3, 9, 27, 81, etc. For 4, we've got 4, 16, 64, 256, etc., etc. And so these are kind of the standard exponentials that we should be familiar with and kind of ready when we see a problem that looks like this, where we've got these kind of big gaps towards the end. So we're kind of looking for something of an exponential. And so let's just kind of take a look at each one of these 3 exponentials and see, is there something that looks kind of close to what we're working with? And so if we look at 2 to the x, so if we think that this has some power of 2 involved, what we can look at is, well, 2 to 1 is a difference of 1. So 2 minus 1 would be 1. And then 4 to 5, that's pretty close. 8 to 7, it's off by 1. 16 to 17, off by 1. 32 to 31 is off by 1. 64 to 65 is off by 1. So between each one of these values, they're off by 1, either plus 1 or minus 1. And so just from noticing kind of this pattern here, we can see, yeah, there's probably a 2 to the power and then something else to give a plus 1 or minus 1. If we looked at others, for example, like the 3 or the 4, you kind of don't see quite that same level of pattern. The 3 and 4 grow at a much more rapid pace for some of those later ones. And so this is what kind of ties us into thinking that there's a 2 to the power involved, right? So what we're kind of thinking is that there's some a to the n is equal to possibly something times 2 to the n plus something else. And what we're noticing here is that there's kind of alternating plus 1, minus 1. So to get to 2 to 1, that's a minus 1. For the next term, 4 to 5 is a plus 1. The next term, 8 to 7 is a minus 1. The next term, 16 to 17 is a plus 1. So we're kind of thinking about this alternating add 1, subtract 1, add 1, subtract 1. And the way that we kind of represent that is we have a negative 1 to a power. Kind of gives us that alternating plus 1, minus 1 that we're looking at. And so actually we're going to have a plus negative 1 to the n. And we can try it out and see, is kind of what we're guessing here, does that really fit? So for a to the 1, if we use this, we'd have 2 to the 1 plus negative 1 to the 1, which is 2 minus 1, which is 1. A sub 2 is 2 to the second plus negative 1 squared. And that's 4 plus 1, which is 5. And a to the 3, 2, 3 plus negative 1 to the 3, 8 minus 1, which is 7. So yeah, this looks like this is fitting. And this is the closed form. And the way we got there is just by recognizing these patterns, looking at the difference between values, trying to see, is this an addition problem, multiplication, are we looking at powers? We noticed we were growing exponentially, so we looked at our powers, then looked to see if we could find patterns. And then we just kind of guessed and checked a little bit. So these are tricky, but it's really about looking for the patterns. If we had a recursive formula for this, then we could solve the recursive formula to get the closed form. But without knowing the recursive, we kind of have to just look for some of these patterns. So did anyone have any questions, other questions on this problem? So we got a question, is it a good way to check for exponentials first, then multiplication, then addition? Yeah, so the reason why I went to exponentials here is because I looked at the difference first. I always think that's a good starting place, because if you look at the difference, between values, that's an easy check to see if it's addition. And that's kind of the easiest sequence to find, is if you're just adding a value each time. And then we can kind of get a sense of how it grows. If they're growing, if it's like a difference between 3, then 6, then 9, then we can see we might be adding some term growing by some multiple. But if we're growing quite rapidly like this, then we could take a look at exponentials. So I might actually do the reverse of what you said, check for addition, because those are pretty simple, and then a multiplication, then an exponential. But for exponentials, really just knowing these kind of basic exponentials would probably be sufficient enough to find some of the patterns in the sequences that we'll be looking at. Yeah, really good question. Any others questions on this one that anyone had? Okay, we'll check out 1B. We can check that problem out next. But just to wrap up problem 6, anyone else have any questions on problem 6? No, looks good. Cool. So let's go ahead and we'll try look at problem 1. So you're good on so A, good, just finding the first 5. So for problem B, what are we asked? We're asked to use algebra in the closed form to determine whether or not the recursive formula is true for the same number sequence, and to show your work. And we need to remember, and it gives us the hint that we shouldn't just check the first few values to see if it works. And the reason why is because that doesn't prove it for everything. We want to show that this formula works for all such values, and you can't do that by checking a finite number. So that's why we have to use kind of a different method. So does anyone have any, I guess let's just take, maybe take like 1 minute for y'all to kind of start thinking about this problem and kind of how you might go about it. Cool. Yeah. And then if you want to type in chat, kind of what how you think we might get started on this problem. So looks like, so Ryan's got a suggestion, substitute n-1 into n squared, then expand. It looks like Jonathan agrees. Yeah, so that's a really good idea. And what I think they mean by that is that, well, what we can do is we know this closed form, right? We know that this is true. And we want to say, hey, is this also true? So what we're really asking is, does a sub n give the same value in both of these cases always? So yeah, what Peter's suggesting, plug that in for a sub n minus 1, and that's exactly what we're going to do. So we can take a sub n, and using the closed form, we'll plug in for a sub n minus 1. What's a sub n minus 1? Well, a sub n minus 1 is n minus 1 squared from the closed form. And then we have everything else plus 2n minus 1. And then now we can just finish going through the algebra on this. So n minus 1 squared, well, that's just n squared minus 2n plus 1 plus 2n minus 1. And well, both the 2n's minus 2n plus 2n cancels, the plus 1 minus 1 cancels, and that's just equal to n squared. And that's exactly what we wanted. We started with the recursive formula, plugged in the closed form, and we got the closed form. So thus, the recursive form is true. And that's just what we had to do for this problem. Start with the recursive, plug in the closed form for n minus 1. See, does that end up with the closed form for the entire function? And it does, so we know that this closed formula is correct. Does anyone have any other questions on this problem for 1b? Awesome, looks like we're good. So any other questions that anyone had on the practice quiz on any of the other problems? If you want to go ahead and type in chat, if you have any other questions, we can go through those. Do we need to remember the table of equations? What table are you talking about specifically there? I assume you're referring to theorem 2. You just want to type in chat if that's the right one that I'm thinking of. Or if you want to unmute yourself and explain kind of what table you're thinking of. Yeah, so what I think you're referring to is just the theorem 2 that lets you show all those equivalences. You don't need to memorize that entire table of equivalences. It's a pretty big table if you remember, so you don't need to memorize that table. And then we have, so question 2, what's the tip off that it should be an implication? Sure, yeah, let's take a look at question 2. So question 2, we've got, so let P denote the proposition it is cold, Q denote the proposition that it is raining. And then we need to kind of figure out how we can write the following in symbolic form. So it is never raining when it is cold. So, and there's already kind of this idea that there's going to be some sort of implication statement here or something. And the kind of so one way, what I like to do at least for this is just to make this clear kind of in my mind is, so let's write out what these variables are. And then we can write out the negation of the variable so we can kind of think about it explicitly that way. So P is, it is cold. Q is, it is raining. And then in this problem, we're thinking it is never raining when it is cold. So we kind of see that there's kind of, this is kind of representing P, and we need it is never raining. So we're probably going to need something the opposite if it is raining. So if we negate Q, then that is it is not raining. It's the negation of Q. But no, it is not raining is not the same as never raining when it is cold. And then we kind of have this weird word here with this when. And so we're not just saying it is never raining and it is cold, it is never raining or it is cold, but it is never raining when it is cold. And so this is really the word, kind of like I was saying, that's going to tip us off that it's going to be an implication. Because we're kind of saying the when is kind of referring to while something else is occurring. And so that's where we get this idea of implication, is we know this thing is true, and that must mean that this other thing follows. And that's kind of where we get this idea that we're using some sort of implication statement here. And the way that we can write that is, so the other way to think about it is never raining when it is cold. We could rewrite that as a different way, as in an English sentence, and we could kind of say that this is really equivalent to when it is cold, it is not raining. Means the exact same thing. If it is never raining when it is cold, then when it is cold, it's not raining. It's kind of another way we could kind of think about this as an English statement. And hopefully rewriting it this way and kind of seeing these P, Qs, and not Qs, then we could see that this statement really is P implies not Q. If it is cold, then that implies that it is not raining. Then Jonathan, you got another question on implication. The implication is only false of P if when P is false and Q is true, right? Yes, that's the only time that implication is false. Is true implies false is false. So yes, you are correct. And then we've got another question. Would it be okay as not Q implies P? So let's think about it. So is this correct? Not Q implies P. Well, let's think about what is this statement saying? This is saying so this is saying we kind of think when it is not raining, when it is not, so this is saying when it is not raining, then it is cold. Is that the same thing as it is never raining when it is cold? Anyone want to type in chat kind of their thoughts on that and maybe why they think it either is or isn't? Or raise their hand if you want to explain that way. Can you repeat my internet? Yeah. So we kind of had this question, is it okay? Is this a valid solution? Not Q implies P, which just means when it is not raining, it is cold. So is that the same as it is never raining when it is cold? Got someone saying no, and then Tori, it could be raining and not cold. Yes. So it could be raining and hot. And that would be fine in this statement when it is not raining. Yes, and Steve is pointing out, yes, that this is the inverse of the statement. And as we've learned in some of the discussions, the inverse is not always true. It's not the same. In general, the inverse of an implication is not the same as the original implication. And that's kind of why. This is saying it's never raining when it is cold, but that's not equivalent to when it is not raining, then it must be cold, because it could have been over here, it was not raining when it was hot. So it looks like that kind of cleared it up. From a few statements back, P implies Q is only false if P is true and Q is true. P is false does not disprove P implies Q. Yes, P implies Q is only false if P is true and Q is true. In other words, true implies false is false. So any other questions on this problem? Cool, looks like we're good. Any other quiz problems? Or any quiz questions anyone else had? Jonathan, I'd like to check 3. Sure, yeah, we can check out 3. So 3, we need to use the truth table to illustrate this behavior. And we need to show the intermediate steps. So to do a truth table, so we've got 2 variables here. We've got a P and a Q. So we need to make sure we have a P column and a Q column. We've only got 2 variables. So if someone's just typed in chat, how many rows in our truth table are we going to have? Yes, Jonathan said 4. Perfect. Yep. So P we'll have a true, true, false, false, and then we just alternate again, true, false, true, false. And then we need to show all these yes, looks like some people have clarified a bunch of stuff there. Yeah, that was all good. In chat. So yes, we got P and Q, and then we're gonna need a not Q. Then as another intermediate step, we're gonna need the P implies not Q. As another intermediate step, we're gonna need the P and Q. And then as our final step, we're gonna need the whole thing. The P implies not Q implies P and Q. So let's go ahead and start filling in. And these will be all the intermediate steps we need. So not Q, so we just negate the Q column. So false, true, false, true. Then P implies not Q. So we want to look at these 2 columns, the P and the not Q column. True implies false. Well, that's false. True implies true. That is true. False implies false. Remember, that's also true. And false implies true. That's a little tricky one. That's true. Just remember, only time, like we said a moment ago, that implication is false is true implies false. Then we've got P and Q, so these 2 columns. So we've got true and true, that's true. True and false, that's false. False and true is false. False and false is false. And then we've got this implication. So we've got the P implies Q, implies P and Q. So we're looking at, does false imply true? That's true. True implies false is false. True implies false is false. True implies false is false. And that's the whole truth table. So any questions? Going through the truth table for this one? Okay, looks like that cleared up Jonathan's questions. Any others? Cool, then we'll go ahead. I want to make sure that we get through this proof problem. So we're going to go ahead and move to that one next. Then while we're going there, if Careless asks if the right of the arrow is true, then it simplifies to true right. Yes, that's one way to think about it.
There's a question.
Oh, sure. Was there another one I missed?
Oh, from the chat.
Yeah, if the right of the implication, I think you mean, is true, then it simplifies to true. Yeah, so what you're kind of saying, yeah, so if we have X implies true, no matter what X is, then that just simplifies to true. Because true implies true is true, and false implies true is true. So yeah, that's one way you could kind of think about it. But we'll make sure we have some time to get through this problem. So this is a problem on proofs, and this will hopefully be helpful in some of these later homeworks. So I'll make sure we kind of look at this. So we've got this proposition that we're asked to prove here. So we've got this thing that if n is an integer, any integer, not divisible by 5, then we need to prove that n has a square that is either the form 5k plus 1 or 5k plus 4. So just take a moment, take about a minute to kind of start thinking about this problem a little bit and how we might go about kind of starting this proof off. Specifically, how we kind of start writing down what our hypothesis is. So hopefully that was a little bit of time to kind of start thinking about how we could start this problem. So we want to remember, so we've got this hypothesis, right? That n is any integer not divisible is divisible by 5. The hypothesis being just the first part of our if statement. So for our proof, we assume that our hypothesis is true. This is how we always start our proofs, right? So the way we do this is we let an integer n not divisible by 5 be given. So we've got some integer n not divisible by 5. We have no idea what that integer is, but we want to go ahead and start with that. And then we've got some ideas in chat about maybe where we're going to go after this. So yeah, we've got some good intuition. We know we're going to do this proof by cases. So we kind of need to figure out where we're going to get these cases from. So we've got this idea we're going to do induction with 2 cases. That's a good idea. That's a good thinking that we might have 2 cases there. We've got this 5k plus 1 and 5k plus 4. There's kind of 2 things there. We actually will have more cases than 2 in order to prove this problem. And we've got another question. Would it be easier to try to prove the contrapositive here? So if n has a square that is not of the form 5k plus 1 or 5k plus 4, then n is an integer divisible by 5. That might be a little bit complicated. It could be, I think it would actually take about the same amount of work to show the contrapositive. But yeah, you could definitely use the contrapositive to prove this statement if you wanted to. But that's not what we'll do here. We're going to do it just normal direct proof. It's a little bit more straightforward in this one, how we could kind of do a direct proof with this. So the one thing we want to think about is we just written down the statement. We have this integer n not divisible by 5. Whenever we're doing proofs, we kind of want to think about opening up definitions and kind of using what we know about what we're given. So we know that n is not divisible by 5. So is there some theorem that we could use that could maybe let us know what does it mean that n is not divisible by 5? If you want to type in chat. Yeah, so Peter, we got mod 4 cases. Yes, Brady, exactly right. We're going to look at the division theorem here because we've got some integer not divisible by 5. So yeah, the division theorem tells us what this integer would look like. So what are the possible remainders we could have for n if we took n divided by 5? Yeah, I've got some ones in chat. Yeah, so it must have a remainder. 1, 2, 3, or 4. Yeah. And just as a refresher, just because it's going to be a little bit important in this problem, I just want to refresh you with what the division theorem is. And so I'll just put kind of like a little note here. Just recall what the division theorem says is that if we have two integers a and b, then the quotient of a when it's divided by b, so we can rewrite a as b times q plus r where q is an integer. And then the remainder is bounded. And the remainder is always either greater than or equal to 0 or less than whatever we are dividing by. So in this case, we took n divided by 5. So b was equal to 5 here. So we know that the remainder had to only be 1, 2, 3, or 4. If it was 0, then it would have been divisible by 5. So that's kind of what tells us from the division theorem why our remainders are going to be 1, 2, 3, and 4. So now that we know we've got these kind of 4 possibilities for our remainders, we're going to use those to build our cases. And why? Well, because we're kind of taking this direct proof approach, we're going to show that there's only 4 kinds of input that we could have had. If n was not an integer, if n was an integer not divisible by 5, it's either got remainder 1, 2, 3, or 4. And for all 4 of those cases, we're going to prove that this statement must be true. Why is it that? Oh, yeah, it does look like a 6. This is meant to be a b here. These two are supposed to be kind of like a little b. And this r here is just less than a b here. So not 6, yeah. So yeah, so we've got these kind of 4 cases. So case 1 then is n has a remainder of 1. And what does that mean? Well, by the division theorem, just like it says here, if n has a remainder 1, then we can take n is equal to (5q) plus 1 where q is an integer. That's just straight from the division theorem. Our first case, n's got to have a remainder of 1. So now I'll go ahead and we'll work through case 1 together, and then I'll give you some time after that to think about how the other cases might work. So we've got this case. We're going to let n be 5q plus 1. And what do we want to look at? Well, we want to show that n has a square that is either the form 5k plus 1 or 5k plus 4. So we want to look at what n squared is equal to. So n squared, well, that's 5q plus 1 squared. And if we work this out, that's 25q squared plus 10q plus 1. And whenever I'm doing a proof, I'm always searching for what the statement we're trying to prove is. Right? I'm always looking, where are we headed? And we want this n squared to be either 5k plus 1 or 5k plus 4. Well, what I'm noticing here is we've already got the plus 1 here. And that looks like what we want here with this plus 1. So we're good to go there. We just need to get some number that looks like a 5k. And well, what can we do to get that? Well, we can factor out a 5 over here on this left side. So we can factor out a 5, and that'll be 5 times 5q squared plus 2q plus 1. And we can rewrite this as 5k plus 1, where k is just an integer. Someone want to type in chat, how do we know that k is an integer? That we can go from this step, 5 times 5q squared plus 2q plus 1 equal to 5k plus 1. Separated by closure, yes. What closure properties are we using specifically here? Yeah, Parker, closed under addition and multiplication, yes. So where k is an integer by closure of addition and multiplication. And so that's our first case proven. We started with the remainder 1. We showed we can get something of the form 5k plus 1. So we got 3 more cases to prove. So case 2, I'll get you started on what that would be. So that's when remainder is going to be 2. Rn is equal to 5q plus 2, where q is an integer. So if you want to go ahead and take a minute or two on your own to kind of work through this problem. So how could we show that n squared, when n is of this form, is either equal to 4k plus 1, or 5k plus 1, or 5k plus 4? So hopefully that was a little bit of time to kind of think about it. And we'll go ahead and kind of walk through kind of what we do. So we want to start with whatever n squared is. And that'll just be 5q plus 2 squared. Then we just figure out what this is. So if we expand this, that's 25q squared plus 20q plus 4. Similar like what we did in case 1, we notice that we've got this plus 4 at the end. Recall we were looking for something, either of 5k plus 1 or 5k plus 4, so it looks like we've got the plus 4 case. So we can factor 5 out these values over here. So that'll be 5 times 5q squared plus 4q plus 4, which is 5k plus 4, where k is an integer, by closure of addition and multiplication. Any questions on working through this second case? Cool. So let's go ahead and we'll try case 3. So go ahead and take a minute or two to think about what happens when n is equal to 5q plus 3, or has remainder 3. So go ahead and take a little minute to kind of work through this case. Then we got a question. So it's the exact same for all cases, just showing that there's remainder r for all cases, right? It's similar. So we're either showing we're showing either it comes out in the form 5k plus 1 or 5k plus 4. And we're just showing that for all possible remainder values that happens. Stuck on case 3. Yeah, case 3 is a bit interesting when we get through this. And if R were 0, then this wouldn't hold true. No, if R was 0, this theorem wouldn't be true. But that's why we were given in our hypothesis that n wasn't divisible by 5, meaning that we couldn't have had a remainder that was 0. And yeah, I guess that's one way we kind of think about it, Peter, that squares either remainder 1 or 4 when divided by 5. Yeah, and then looks like Brian kind of has a little suggestion about where this issue comes up in case 3. So let's go ahead and go through it. So here we've got n squared is equal to 5q plus 3 squared. That's 25q squared plus 30q plus 9. Well, here we've got this plus 9 at the end. That doesn't look like a plus 1 or a plus 4, right? So maybe this theorem's false. And we're going through this case, and oh no, we found this plus 9. It's looking like it's not going to hold. But what we want to remember here is what we're kind of thinking about, and what Peter's on the right track to is that we're looking at kind of this, what we could kind of think about this problem is asking is, when n squared is divided by 5, we want the remainder to either be 1 or 4. And so what we can use then is we can use the division theorem as a way to rewrite this plus 9 in terms of a 5 times something plus whatever. And the reason we're doing that is because we're looking for these remainders divided by 5. So we're looking for some values between 0 and 5. So what we can do here is we've got 25q squared plus 30q plus, and this is really 5 times 1 plus 4 by the division theorem. And now we can factor, now we've got the plus 4 that we wanted. We can factor a 5 out of this. And we've got 5 times 5q squared plus 6q plus 1 plus 4, which is 5k plus 4, where k is an integer, by the closure of what we said before, addition and multiplication. And then, yeah, so Brian's suggesting case 4 is going to be similar. And yeah, it is. So let's take a look at what happens. Let me get to a blank page here. What happens with case 4? So in case 4, we've got n is equal to 5 q plus 4. And then n squared, that's just 5q plus 4 squared. 25q squared plus 40q plus 16. Oh, we've got the 16. That's not a 4 or 1. But we can use the division theorem to rewrite 16 so that we get a small value between 0 and 5. And 16, that's the same as 5 times 3 plus 1. And that's by the division theorem. Now we've got the plus 1 that we were looking for. We can factor the 5 out of here. So that'll be 5 times 5, q squared, plus 8q, plus 3, plus 1. That's 5k plus 1, where k is an integer, by the closure of addition and multiplication. So a little trick here, case 3 and 4, is we needed to kind of rewrite these values, factor out a 5 using the division theorem, so that we could get the remainders that we wanted. So we could show it was either 5k plus 1 and 5k plus 4. Any questions on that right there at the end with those cases? No, it looks good. Cool. And then after we've done, so we've proven all 4 of the cases we were asked to prove for each of the remainders 1, 2, 3, and 4. So Jonathan, why exactly did it need to be 1, 2, 3, 4? Yeah, great question. So remember, we were asked to prove that if n is an integer not divisible by 5, then we need to prove this. So there's only 4 possibilities if n is not divisible by 5. It either has remainder 1, or it had remainder 2, or it had to have remainder 3, or it had to have remainder 4. And then what we did is we just went through each 4 of those possibilities to prove that it was true. And we had to show all 4 of those possibilities were true. So that way it's true in every case, so the whole theorem is true. And then once we've shown all 4 of those cases, we just kind of need to write just a final statement concluding this. So we can write therefore, we have shown in all possible cases where n was an integer and not divisible by 5, that n squared is of the form 5k plus 1 or 5k plus 4 for some k. That's an integer. And then we can either put like a square, QED symbol or something as to conclude our proof. So we're about out of time. Did anyone have any quick questions before we head in and go? Yeah, proofs are hard. Yeah, they just take a little bit of practice. They're a little bit tricky right at the start, but the more you practice proofs, the more this is going to become a more natural process. What does QED mean at the end of proofs? It's a Latin word, and it means like what was asked to be shown has been shown. So it's just to kind of point out to your reader, same thing with the square at the end, that your proof is done. And what we wanted to prove has been proven. No class on Tuesday, right? No, there should be class on Tuesday. It's just Monday. Yes, there is no recitation on Tuesday because of the quiz. Yes. And then don't forget tomorrow and Monday, there'll be some quiz review sessions. So there's a bunch of times tomorrow, and then the one on Friday or on Monday is mine, which would be from 3 to 5. And then the quiz will be Tuesday. So just go ahead and check the module section on Canvas for some of those review times. And yes, I do have office hours. Yes, even with the holiday on Monday, I will have my office hours Monday from 3 to 5. Zoe's were moved to Friday, I believe from 10 to 12. So tomorrow, so you'll have her office hours. Awesome, then I'll go ahead and let everyone go. So good luck on the quiz next week. Hope you all do well.